All right. I'm first very thankful that the organizer has invited me for this talk. Today I'm going to speak on the AI for digital health. This is a topic that is actually very interesting to me because I have started working on digital health related projects now several years ago, and so after these years, I realized that there are some interesting opportunities but as well as some challenges which I hope I could share today. And maybe this experience could be useful to other researchers when they pursue research, applying AI to digital health. Okay, what is digital health? I would like to borrow Singapore's Health Science Authority's definition. It is defined as the use of connected devices, wearables, software, including mobile apps, as well as AI, to address the health needs via the information and communication technology. So this is a very general definition, which means that there could be many applications in the health-related areas that could make use of ICT. And particularly, I think in today's talk, I would like to speak a bit more about the use of AI. Right. Now, why do we care about digital health? I guess one important trend we are seeing in all developed countries is that we are now aging quite quickly, right? In the case of Singapore, you can see that the proportion of people reaching the age of 65 and above is now near, let's say, 10%. Or actually higher than 10%. I think by the time we reach the 2030, it will be 25%, which means 1 out of 4 Singaporeans will be of the age 65 and above. This is very scary. In the case of Taiwan, I think based on what I found in a paper dated in 2006, it was said that by 2030, Taiwan will also have about 20% population of the age 65 and above. And I think these studies may have to be updated from time to time, and maybe the actual figure is higher than we expect. Now, with agings and with other issues such as medical costs escalating, and also the importance of physical and mental well-being, means that we have to care more about the digital health, and we have to find ways to use digital technologies effectively to improve our health. Now, of course, this is a big topic, and also I think if you look at the development of AI research, we can see that many of us who work in AI topics, right, have seen a lot of publications generated by the AI communities, the research communities. And there's also a lot of interesting real-world solutions that has already been demonstrated in the area of AI. And of course, other than the real-world solutions, there are also a lot of interest, right, in the academic research, right? Not necessarily in computer science, but in several other disciplines. These are all opportunities for AI research to create impact on, right? So at the moment, I think unfortunately we are doing a lot of work in publishing papers, but maybe in terms of generating real-world solution and making impact to academic research outside the computer science discipline, we still need to do a lot more. Otherwise, I think our impact will still be limited to just papers, right? So in today's talk, just to make it more concrete, I will decide to focus on the food visual AI. This refers to the AI technology that is used to recognize food or to process food images, so as to help us, achieve certain application related to digital health, and also to help us create the right technologies to conduct academic research, right? For example, in healthcare domain, public health domain. Now, in this particular talk, I will focus largely on the food image recognition as well as a food image segmentation. right? So food image recognition refers to the processing of the image using AI and then to predict the food in the image, right? Now, food segmentation refers to um, identifying the different polygons that represents the different ingredient of food, right? So both are clearly the AI problems, and so we spent several years of effort doing work in this topic. Now, unfortunately, the journey of trying to turn our research into a real-world solution as well as research tools are not so straightforward, right? So today I'm going to share a bit this journey. Okay, so let's talk about the first story. This is about the food image recognition. As I've just said, right, the food image recognition problem is to take an image and develop the AI to predict the name of the food in the image. So in this slide, now we have a burger image. Of course, we need the AI to be able to predict this is the burger. Now, for a human being, this is a very trivial task. For AI, I think it's a bit harder, and at the beginning, I think sometime in 2016, we started some research on food AI, which is the technology to recognize food. We started with 101 different food classes. These are basically the food classes that we identify from some images that we can crawl from the web. And so with this 101 food classes, we try to crawl, we actually crawl about 200,000 images and label them. So we hire some poor students to label the images for us. And then we developed the first model, the Full AI version 1, which can achieve a pretty decent accuracy of 97%. All right, this is top 5 accuracy. Top 1 accuracy will be slightly lower. Um, of course, as researchers, we are excited with this accuracy, and we subsequently. I'm sorry, is there any problem with sound? I can hear echo.
Yes, Professor. We are hearing echo here too.
Should we do some checking?
It's already fine now.
Okay.
You may continue.
All right.
Thank you.
So sorry for the interrupt. So with the high accuracy, we thought that it would be good to start engaging some user. So we talked to Singapore's Health Promotion Board and show them our results. Of course, the Health Promotion Board, in short, we call this HPB. They are very excited, but they give us a challenge. They say that, obviously 101 food classes are too few for real-world use. I guess we all understand why, because in Asia community, we are spoiled by many different kind of food choices that we have. So obviously, the number of food that we can consume can go beyond 100 easily, right? Now, of course, we know that if you want to cover more food, we need to collect more data. At the same time, we also know that the accuracy of recognizing food will go down if we increase the number of food classes. Now, so the immediate problem then is that how do we gather more images and label them so that we can expand the set of food that we can recognize. So the first solution that we developed is to create a system which is called FAMS. It stands for Food Annotation Management System. Now, the purpose of creating this system, FAMS, is that it could help us, scale up the way we collect images of food, right? So the way we do it is that once we know that we have a certain set of food that we want to collect images, then we input all these food names to FAMS, and FAMS will take care of the crawling of these images on the web. And so we do not need to manually, find a way to crawl the images. And the images after being crawled will be assigned to the annotators for annotation. And in this case, the annotation task is assigned such that each annotator is required to annotate images of the same class. All right, so this will speed up the annotation task. All right, so from 101 food classes, we now increase to 756 food classes, and so this is what we could quickly achieve, but of course with the help of another system. Now this is an image that shows how this FAMS looks like. So as I just said, if you want to label, if you want to collect images about orange juice, we could input orange juice as a keyword, and the FAMS will go out and crawl the images, and then the images would then be assigned to the annotators for labeling. Okay, so so very quickly we gather 400 over 1,000 food images and label them. So this is a much larger data set now. Now, of course, the problem is not just there, because as we collect more food images and label them, we realize that there's some complexity that comes with these images. Because a lot of this food comes from different ethnicity. Some are from Chinese cuisine, some are from Indian cuisine, and some from Western cuisine. So they cover many different kind of recipe. And sometimes for the same food, we give them different name. For example, this particular food, I don't know whether you can find in Taiwan. It is in Singapore, it's called Hokkien Mee. It's also called fried prawn noodle. So when people think about this food, they can give any name to it. So so this could give us some issues. So if we have included accidentally included two food names that actually refer to the same food, then that's not good, right? So we have to fix this problem. And then we also find some food they are different, but they look different. They look similar. For example, pizza is a Western food, and prata is an Indian food in Singapore. Sometimes people may confuse between them, right? If you look at the image, they are both round. They looks like some kind of they look sometimes similar. All right. So these are challenges, which means that we have to train a model that can differentiate them. Another challenge is that the images that we gather are imbalanced, right? So we have 756 classes and 400,000 over images. And if you look at the distribution of images among the 756 food classes, it is clearly imbalanced. Some classes have a lot of images. Many classes has very few images. All right. So this is this could be a challenge, right? When we train a AI model to recognize food. Now, what we could do, of course, when we collect the data and labeling them, we ensure that for the most popular Singapore food classes, the 100 of them, we ensure that there are at least 500 images for that food classes. This is to ensure that the popular food can be recognized more accurately. Now, of course, we need to do some experiment with different models so as to see whether we can get high accuracy from the recognition. Here are some models that we have developed. Actually, instead of develop, we are saying we tested on them. Right, these are actually known models out there. So we realized that the SENet, ResNet actually achieved very good accuracy in our experiment, but the other models are not so accurate when it comes to top one accuracy. Now, what we have done is that we introduce a new loss, right, called focal loss. And with focal loss, we can effectively improve the accuracy of all these existing models to pretty good level. So at the end, we realized that achieving 95 or close to 96 accuracy for top 5 and 83% accuracy for top 1 basically can be done, right? So we have we think that that's not a problem for now for handling the food recognition. Okay, so with this 756 food classes, we finally trained another model, a model called Food AI version 4. This version 4 performed very accurately when we tested on this new dataset, Food AI 756 dataset. Top 5 accuracy is 95.9, top 1 is 82.5. Okay, so this is pretty good, and actually our agency HPB was very happy about it. So we started to deploy this model, and this version 4 is licensed to HPB and deploy for quite some time. And then the idea here is that we create an API, Food AI API, which receives the images from the mobile apps developed by HPB. And whenever we receive an image from the app, we will return the top 5 predicted food classes back to the app, so that the app would then receive this information. Now, what this app is trying to achieve is to help user perform logging of their food consumption. So for example, if you install the app, you'll be able to enter what you have eaten for breakfast, for lunch, and for dinner. Of course, you can enter the food by typing the name of the food, right? But with the help of Food AI, we have simplified the process significantly, because the user just have to take a picture of the food they consume, and then we can automatically return the name of the food, right? So that's simplify the task of logging food, right, significantly. Now, is it considered job done? So we tried for a while, and then what happened is that the next challenge come, right? So this challenge is that we realized that the food that we collected during the deployment are very different. The images are very different from the one that we have used for training our model. All right. First of all, we receive images that are non-food, right? Some naughty user take pictures of other things, right? They are non-food, and send the food images to us, right? And then, of course, we are not able to recognize them properly. And then the other problem is that sometimes when we train our model, for example, when we train the model to recognize soya milk, right? So this is our soya milk images when we train our model. But when user send us the soya milk images, they appear like this. So they appear in the package form, which we didn't expect. Okay, so there are several other these kind of issues that we encountered during the deployment, and based on our experiment on this so-called production images, the accuracy has dropped significantly for Food AI version 4. So from top 5 has dropped from 95 to 77. This is quite a significant drop. Top 1 is even worse, from 82 to 45. All right. So we have to do something. All right. So what can we do? Before I show you what we have done, I show you more images that tell you how challenging the live deployment is. So for example, you can see that in this image, we have several images of coffee and tea, right? I'm not sure how Taiwanese drink coffee and tea. In Singapore, when we drink coffee and tea, very often we add milk to it, right? We add milk to coffee, we add milk to tea. I think this is influenced by the British, in the past. Now, as a result, coffee and tea looks the same, right? So you can't clearly differentiate which one are coffee, which one are tea, right? So this is a challenge. We refer this as the inter-class similarity. And then there are also another kind of food called mixed rice, right? Mixed rice is a very interesting food, right? It actually is consist of rice plus a mixture of other dishes. It could be vegetables or meat dishes and so on. Because it is so diverse, right? You can find different kind of vegetables, different kind of meat in mixed rice. So the look of mixed rice never appear to be very similar, right? So again, we have a lot of different type of images of the same food that we need to cope. Now, of course, there are also another issue that some people take picture of their food after they finish eating the food, right? So that's not very useful to us, right? So these are again some kind of naughty act. Now, there are other kind of deployment images that makes recognition challenging. Sometimes the resolutions are poor, orientation are wrong, and then sometimes people take pictures of multiple food together, thinking we can recognize them, uh, and unfortunately we couldn't. And obviously there are also images of other strange things, right? Okay, so this is what happens when you deploy your technology in the real world. So obviously with this, we know that version 4 of our food AI is not good enough. So what can we do? So we now have to start thinking about using production images to train our food AI model. All right. Fortunately, because the way we deploy food AI is to develop a API, and the API runs in the university machine. So we are able to collect the food images through this deployment, and all these food images are available to us, but they are not labeled. They are still unlabeled. So we have to find a way to label these images. All right. Now, of course, in this process, we have to select the food classes that require further training, because the production images are very different from our training images, and that affects and also affecting the accuracy. So we have to select food classes that need further training of food AI, and further annotation by user, all right, our annotators. And so in this case, we selected these images and made use of the FAMS again to assign the task, annotation task, to the annotators, right? Now, this time around, we know that there's some non-food, so we use a new class called non-food class, right? And then and we assign these images to the annotator. Some of the minor things is that because the production images are not labeled, so we don't know what this food, each production image is about. So we have to use our top 5 prediction using the food AI version 4 to see whether some images could be potentially belonging to the target classes that we want to annotate. All right, so we have to do something to select the images to be annotated. Okay, so with that effort, we have annotated another 90,000 images. These are production images. They are still under the 756 food classes. And actually, altogether we have annotated more than 10,000, 100,000, another 100,000. And with this, we trained a version 5. That was in 2021. With a better backbone, so as to hopefully improve the accuracy. Swine-based is used. Now, let's look at the accuracy. So version 4, this is the version 4 results. Very poor performance for the production images. Now, once we have created version 5, and we managed to improve the accuracy significantly to 84 for top 5 and 57% for top 1. Up to now, this is still the best performance we can achieve. And so version 5 is now pretty decent, and it can be used. So with food AI projects, at least based on what I've shared, all right, so we know that food AI version 5 is pretty good enough for real world application. And indeed, we have already started using this in the HPB. HPB is already using version 5. And also with version 5, we are able to support some user studies on food consumption behavior related to obesity, and also to compare the different modes of food logging in both NUS and SMU. So this is the first attempt to take our technology and use it in academic research. Now, the licensing has also started to be more and more popular. So up to today, we have received many inquiries, and about 140 people have already licensed our technology. And out of that, there are also 3 commercial licenses that we have realized. So the lesson learned here is that when we do AI research, right, in the university, we may not be anticipating some of these challenges when we need to address, in the deployment. And there's also a lot of engineering effort that has gone into this effort. Now, why we spend all this effort beyond writing papers? Of course, one objective is to put our technology to use. The other reason is also that throughout all this work, we are funded by agents by government, which set the API, the KPI, the key performance indicator, including live deployment. So we have to do such a kind of work anyway, as part of the grant that we receive. So of course, looking forward, there are some future things we can do. We can anticipate that there will be more and more food classes that we need to recognize, and so this can be achieved by some of the newer AI technologies, the few-shot learning, one-shot learning, and even lifelong learning. Right. So this helps us to overcome the data barrier and perhaps to also adapt the AI model to different domains. So the Food AI is currently available for developer. So this is the URL www.foodai.org. You're welcome to try out this the demo and perhaps also to use the API. I think it should work for the food that you find in Taiwan for most of them. Okay. Now, of course, there are questions about how is Food AI compared to Google Lens. Google Lens is a technology developed by Google. It is very competitive based on what I've checked out. But we also see there are some differences, right? So let me just show you some examples. This is a minced pork noodle in Singapore. I find that for Google Lens, somehow it recognizes it as another Indonesian noodle dish. Which may look similar. So you can see that in this context, right, in this example, if Google Lens doesn't know that this food image is from Singapore, is one of the Singapore food, then it may predict the name wrongly. This image is called fried kway teow. In Chinese, it's chao guo tiao, right? Google Lens somehow could not recognize it. It can predict national dish. I don't know national dish for which nation. It's not clear. This is white carrot cake. For Google Lens, it cannot predict anything. For this food, which is Indian food in Singapore called putu mayang, but Google Lens predict it with a different name, Adiyapan. Right? This is another noodle dish in India. Right. So I think based on this simple comparison, we think Food AI is still pretty decent. At least it does not it performs well largely because of not only the model but also the data set that we have used. So let me just quickly share the second story. This is the story about food image segmentation. And the model that we train is called Food AI Plus. Okay, food image segmentation is to take an image, recognize the ingredient in the image, and try to identify the polygons that cover the different ingredients. Take, for example, here we have a bread roll, we have a tomato in the image, lettuce, beef, and so on. So we want to be able to recognize all these ingredients. Now, as you can suspect, right, this is going to be a more challenging task because we are not predicting the food of the image, but predicting the different parts of the image, right? How to find the parts and label the part and predict the label for the parts is indeed the challenge that we need to address. Now, of course, like the Food AI problems, we need some label data to train the model. And in this case, the labeling effort is going to be more challenging, more costly. But of course, some people may say that why not just draw something rectangle, right, to cover the different ingredient. Now this is easy, but then it will basically create a lot of imprecise sort of polygons, right? So we chose to use a more fine granularity kind of polygons to predict the ingredients. Now, first of all, we need to decide what ingredient that we want to cover. So in our study, we started with 103 ingredient classes, right? How do we get there? I'll share a bit more. But even if we decide as we decide the ingredients, we also notice that there are some challenges, right? The challenge, of course, our intent is to get a data set for training the model. We first scan around, we could not find high quality food image data sets that has got the image has got the mass. Mass refer to the polygons of the ingredients. So we don't find a lot of label data set for us to train our image segmentation model. And also, I think if you look at the images of food, right, and look for the ingredient to recognize, you realize that sometimes ingredients are not easy to recognize. Take for example, how do you recognize the ingredient water? Water is an ingredient of food, but then you can't see it, right, in the when the food is prepared, right? And sometimes ingredient may overlap each other. All right, and then sometimes the same ingredient may look very different. For example, pineapple in this dish and pineapple in this plate are very different in appearance. And sometimes the potato, right, may look like pineapple, right? So these are complexity in the problem, right? So first, let's address the data set problem, all right, the data set challenge. So we started by looking at this data set, recipe 1 million. This is a famous data set that cover a lot of food images, close to 1 million food images. And the good thing is that there are ingredients that can be found in this data set. So altogether, there are 1.5 ingredients. But among these many ingredients, I think we can only take care of about 103 ingredient categories. And the other ingredients are considered as others. All right. And we also grouped the 103 ingredients into 14 superclasses. Altogether, we also selected only 7,000 images for annotation. Now, notice that the annotation is going to be challenging. To make sure that the images are well selected for annotation, we also select the images with at least 2 ingredients but less than 16 ingredients. How do we know that? Because we have the recipe information, so we select the images accordingly. Now, we also hope that the ingredient should be visible, so we confine ourselves to the visible ingredient, right? If the ingredients are too small, difficult to spot, we will give up the ingredient, right? And we paid a company to do this annotation. This cost us a few $1,000s. Okay, so here are the example of the images that we have labeled. So you can see on the first column, these are the raw images, and the second columns are the corresponding label images, right? Okay, so this data set is called Food Segment 103. This is called the Food Segment 103 data set. This data set is open to other researchers. You can actually download this data set from us. Now, Food Segment 103 data set cover mainly the Western food. So to add some Asian food images to our data set, we selected another 2,000 over images and annotate them. So this becomes our segment 154 data set. So the 154 data set has more cover more ingredient now because of the Asian food, right? So we have 154 ingredients covered by the food segment 154 data set. Okay, so this is just a table of statistics for the 2 data set. I have also included 2 other data set, UEC food and UEC food data set, which are also used for food segmentation research. And you can notice that we cover a lot more ingredients as well as images wise. We are also quite big, all right. And mass wise, I think we cover a lot more mass. Mass refer to the polygons of ingredients. So our data set is pretty large. So you can see in the food segment 103, here are the more popular ingredients. So bread, you can find bread a lot in the food segment 103 data set, tomato, strawberry, pork, and so on. Now for the Asian food, which is the additional Asian food images that we annotate. The more popular ingredients are noodle, vegetable rape, and rice, and lettuce, eggs, and so on. So this is not surprise because for Asian food, we eat a lot of rice and noodle, and so they are the more popular ingredient. Okay, let's talk about the accuracy. How do we measure accuracy of food image segmentation results? So if we have a source image, I think here we have a cake, a piece of cake. So the correct mask is shown here. All right. So this is what ideally we want to be able to recognize, and sorry, we want to be able to segment. If our model produce these results, which is a different polygon shape, right? This is our predicted mask or predicted polygon for the cake. Then we can measure the accuracy by looking at how much overlap is between the predicted mask and the ground truth mask. Okay, so there are two measures that we introduced here. One is called the IOU measure. The other one is the accuracy measure. So IOU measure is to take the overlapping pixels of the two masks and divide by the sum of the pixels of, that means union of the pixels from the two masks, right? So so we compute this for every ingredient, and then for all the ingredients we can compute a mean IOU and a mean accuracy. Okay, so that's how we measure the accuracy. Now, with the accuracy measure, we start evaluating several different models. So here are the different models that we have experimented. And CCNet, FPM, and the SCTR. These are the well-known segmentation or state-of-the-art segmentation model, and they all use some kind of backbone. So here we use the LSTM. Here we use LSTM. All right. So we notice that the performance of these various models, of course, are not as high as 90%. Actually, average, right? They are about 30-something% or 40%. The best we can achieve here for these few models is 43.9% for IOU, MIOU. Okay, so anyway, we proceed to develop Full AI Plus, version 1, version 2, version 3, based on the different models. And finally, we get a version 3, which achieve MIOU of 53 and a mean accuracy of 62%. This is the best we have achieved. Okay, and so this is all trained and tested on this food segment 154 data set. So again, once we have got this result, oh, by the way, this is a slide showing the last version 3 model. It's based on mask-2 former, which has a model that model setup that looks like this. I will not get into the detail, just to let you know that it's a pretty complex model. It requires a backbone and a pixel decoder to decode the images at the different level. And it also has a transformer decoder to help us predict the different ingredient classes. Finally, we need to use the ingredient classes that we predict and combine with the pixel decoder so as to predict the right label for every pixel. Okay, so so here we have a version 3. All right, so we have a version 3 Full AI Plus model, and now as we show this to our our HPB agency, we have again come back with this challenge. How do we cover more ingredients, right? So you notice that this kind of challenge keep coming back. And of course, we have to think about our solution, right? So one solution, which is a straightforward solution, is to collect more images and label them. Okay, label more food with new ingredients. But this will mean that we have to spend a lot more cost on the doing annotation, and this process may also take time. So how do we overcome this challenge? Now, some of the new ingredients that we want to cover include these 48 categories. avocado, dragon fruit, Singapore, famous durian. And so these are the new ingredients that we want to cover, right? So we need to find food images that cover these ingredients and get people to label them. Okay, so how do we label this new ingredient? So instead of repeating what we have done earlier, now we get our annotators to just focus on annotating a single target ingredient. Take for example, suppose I'm interested to introduce rice as a new target ingredient, right? And so instead of annotating, getting the user to our annotator to label all ingredients in the image that contain the rice, I would tell the annotator just annotate the rice. Forget about the other ingredient in the image, right? So in this case, there are much less work to do, and the annotator can just focus on the rice, right? So for the second image, this will be the polygon this will be the mask for the rice, and the rest can be ignored. And the third image as well, right? So we'll ignore other ingredients in the image. Now this is a way to reduce the effort and speed up the annotation, right? And of course, we still have this other question: how do we find images that contain rice? So to do that, the good thing is that we have Food AI. Food AI allow us to predict the name of the food given an image. So for example, for this food, we may predict this as a chicken rice or something. All right. So since the name of the food is chicken rice, then we know that it should be rice in the food, right? So this is our based on our recipe knowledge. So since we know that the chicken rice has rice, then we can set image to the annotators responsible to annotate rice. Okay, so there are some other things we need to do, use of the Food AI technology that we have built. Okay, so with this, we created a new dataset called Food Segment 198 dataset. It now cover 198 ingredients, a lot more images now. Okay, a lot more masks now. Okay, so this is our new dataset. Now, with this new dataset, can we just directly use it to train our segmentation model? We can. So we did an experiment. We trained our Food AI version 3 on this new set of images. But we have a problem, right? You can see that here is the problem. Here is how it looks, right, in the result. So given this test image, right, if I apply the trained Food AI using the 198 dataset, it will predict this mask, right, for the bun of the burger. It does not predict the rest, the other ingredient, right? Now, of course, this is a very funny result. Food AI is supposed to predict all ingredients in the image. Now, the reason why Food AI version 3 failed to predict the other ingredient over here is that all the images that it has used for training the recognition of the bun, right, only contain the bun polygons, right, and no other ingredient polygons was found, right? So as a result, it has been trained to only recognize bun in isolation. It does not recognize bun in the mixture of other ingredients. So therefore, our model does not work if we just want to directly train on this the new set of images that we have annotated. So what actually we want is to be able to predict all the ingredients. So what can we do? So we introduce another solution called the self-training strategy. So the way self-training strategy works is that we first train a model recognize the ingredient in the food segment 155 dataset, which we have said earlier. So we have this Food AI Plus version 3. And then for any image, right, that we have newly annotated under the 198 dataset, we know that there's going to be ground truth mask, right, in this image. And this ground truth mask cover only one ingredient, right? So for example, in this image, the ground truth mask only cover the ingredient of bun, right? the burger bun. Now, so we take this image and go through the segmentation by the full AI version 3, and this is our predicted mass. Okay, this is our predicted mass covering different ingredients. So since we have the predicted mass and we also have the ground truth mass for the bun in the image, we merge the two mass together. So the predicted mass that covers the bun area will be replaced by our ground truth mass. Okay, so this is our new self-trained image, which basically consists of a mixture of predicted mass as well as the ground truth mass for the bun. And with this self-trained image, we train our model, right, using the merge mask. All right. So so this is our self-training strategy. So this is to combine predicted mask together with the true mask so as to train a model. So we train the model in this manner using self-training, and then what happened? Notice that after this, our Food AI Plus version 3 trained using 198 dataset and using with the help of a self-training strategy, we can achieve the MIOU of 0.7 and mean accuracy of 60.3, which is not as good as the result we obtained using for dataset, but still quite close, right? Quite close to the results. And in fact, for the new ingredient that we have added to the dataset, the IOU, the accuracy, are even higher, much higher, significantly higher. All right. So this is encouraging. That means our self-training strategy must help us to overcome the challenge of the new label dataset. So Food AI Plus is also available online. So you can see that here are some images that are tested. So for the image below, you can see that this is the French toast with strawberry and blueberry, and even and I think this is what I can find. Our segmentation model predict blueberry, red, and strawberry, and even I don't know where the cherry is, but anyway, this is how the result looks like. So what are the lessons? Okay, so here are some points. The first is that as we expect, collecting data and labeling them for training AI models are real challenges, and I don't think we can escape this challenge. So I think if you are interested in applying your AI model to real life problems, you need to be prepared to spend some effort in collecting data and labeling the data. The good thing is that we have also developed some technology like FAMS to help us perform this task. And we also learned from this full AI effort, right, that we can use the single ingredient application approach to scale up the labeling effort. And self-training strategy to train a model with a single ingredient annotation is proved to be quite effective, right? So it is a good strategy for us to quickly incorporate new ingredients to existing Food AI Plus model. Now, immediately after this, we know that the Food AI Plus can be used in also other projects. For example, we know that in the hospital, they are very interested in analyzing the consumption of food before and after consumption, right? So this is important for checking out whether the patient in the hospital consume enough food, whether they have eaten, for example, vegetables or carbohydrates. So this is one important study that the the hospital would like to conduct. Then, of course, you can use the technology to study whether people's study the people's diet and so on. Now, we can also use this to analyze eating behavior. So again, HPB is interested in that. So to conclude, I think here are the takeaway points. I've shared with you the full AI class story. It's a long journey because it takes almost like 7 years for us to go through this research and as well as technology development. So if you are on this track, you need to be patient. You also need to collaborate, and also it's important to develop a system platform for technology and to deploy the technology because deployment may only be possible if you by the university in this when you first develop the technology. Now, for young faculty who has not got the tenure, I don't think it's something that you want to do. Perhaps for tenure faculty who are more experienced and they have secured a job, so then I think it's good to it's something that you can try out. But this is also an effort that you need a lot of funding support. So I think if there's any funding agency listening to this talk, I would like to urge you to be generous, drop more money to this kind of project. At the end of the day, such projects can also be rewarding because not only we generate publication, we will see the development of system. At the end, there will be a team that is formed. Okay, so I think that summarizes my talk. I hope that this talk can inspire more people to work together to turn more AI research into digital health technology. Okay, there are some papers that I could share here. The talk is very much based on 3 papers, one at KDD and one at CBPR, and the other one is a multimedia paper. Over here, you can see that I work with many distinguished collaborators. Stephen Hoy, particularly, and Professor Sun Chen Lu, both are faculty of our school, and there are several other PhD students, postdocs, who contributed to this work. Finally, I thank you for listening to the talk and would like to hear any questions.
Are there any questions for the keynote speakers?
Professor Lin, I'm very impressed by your research. I think that's a long journey. It's several years ago and tried to put that into a very relevant issue, which is affecting our daily life, our eating. One of the curiosity I may want to ask, and I can have some to share with that. It's for the ingredient detections. So in our Asia food, we tend to calculate. Okay, means we cut all the different meat into different size, different shape. For example, we have a chicken calculate, and we have a pork calculate. And then I'm not sure that will you in your model also consider that able to differentiate this is pork and this is a chicken, or it just mixed together.
Yeah,
right
yeah.
now.
Yeah. Yeah, that's a very good question. I think when you see the Asian food, right, you find the ingredient has been prepared in so many different forms, and obviously some of them can make it challenging for us to recognize, right? So we know that that is a challenge. So I think if the same ingredient remain to be visible in the image, we will still be interested to predict the segment that cover the ingredient. Now, only when the ingredient becomes hardly visible, all right? For example, let's say, I mean, there are many ingredients that are almost invisible, right? For example, salt, pepper, some kind of sauce, right? Soy sauce. They are completely if it's, I mean, difficult to see, right? Then we have to give up on this kind of ingredient, right? And if you so we have to we have to compromise to select a subset of ingredient that can still be visible in the image. So this has taken some time for us to determine such those ingredients that remains to be visible. And also for the annotation purposes, we also advise our annotators to annotate as detailed as possible for those visible ingredient. So even when the ingredients come in the form of, let's say, minced, right? Minced pork, right? So we will still, if the minced pork is visible in the food image, we still want our annotator to be able to mark out the mass for such ingredient. So this is what we have done. So for example, here is an ingredient called the minced leaf, right? For example, and even though it is difficult, right? You know the shape is odd, right? But we still want our annotator to create a mask for this minced leaf, right? Because we know that it's still visible, so we have to include it. All right. Now, unless this ingredient is not covered by our dictionary of ingredient, all right? Otherwise, we will still need this to be annotated. So that's our underlying principle. I hope it answered your question.
Thank you.
Is there any other question?
Oh, yes. Professor Lee, okay, I have one question which is may not directly related to what you just presented. I'm working with luxury bag, secondhand, used luxury bag trader. Okay, and so she wants to know whether we can use technique that you just presented to identify whether the bag is a fake bag or it's a real bag. It's a Gucci or it's luxury bags. It's very expensive, and so they don't want to even though they can identify most of them with maybe 95% of them correctly. And he want to know whether computer or this kind of technology can help them to identify the rest 5%, or at least use computer to identify most of them, and then reduce human beings slowly. And by using this technology that you just present, would that be a very different things? Just curious because I'm not in this field.
Yeah. I'm also not an expert in bags, especially ladies' bags. I think the problem is similar. I would think that the problem is similar. Now, of course, just like food images, right? So when you have a more detailed image, you will be able to recognize the food more easily. So I believe the same applies to recognizing fake versus the genuine bag. If you have a very high resolution image, you probably will be able to differentiate them more easily. Now, so in the case of food images, I think when we first tried our original 101 data set, it was the result was very good. The accuracy was high. Also largely because most of the images we downloaded from the internet are very high resolution, especially when people share images of food on the internet. They usually are the bloggers, they are the food lovers. They take very nice picture of food, right? So those food are easier. Those images are easier to recognize. All right. But when it comes to the live deployment, as I also share, those images are of poorer quality. The angle of shooting could be very poor, right? The lighting can be very poor. So all these contribute to challenges in recognizing the images. So I think the same applies. for genuine and feedback kind of recognition, right? Although I can't tell how accurate it could be, I think someone should try and see how it works.
Okay, thank you.
You're welcome.
If there is no other questions, we would like to thank you, Professor Ee-Peng, for his presentation today. Please give him a round of applause.
Thank you for the